So to make the link with the previous presentation, I'm going to ask you this question, and I want to have your opinion, and maybe after we can ask Dave on that. So how can you trust natural data when, as Dave showed us earlier, the nature has so much more complexity that can potentially be misinterpreted?
Yeah, that's a really, really important point. What I would say is that, as I put forward, if you see something that's repeated and consistent, then I would argue that's trustworthy. Whether that represents, I've argued it generally represents a thermodynamic equilibrium control, whether there's the possibility that parts of it could be a kinetic control. It's still a pattern that we want to aim to reproduce in our modeling and explain in order to get the right answer when we're making our tectonic interpretations. So I would hope that whatever this data represents, the compilation itself is the truth, it's nature, and whatever goes into deciding the compositions and the assemblages that appear in these natural sequences, we can figure that out from there. But I'm sure Dave Patterson has comments, and yeah, I don't know. We can open it up, I'm sure, and Dave can correct me or fill in the blanks.
We are reaching exactly the end of your dedicated Q&A session, Jacob, and it's the perfect time now to ask exactly the same question to Dave.
Okay. Well, first of all, I think this is such an important question. It's the interface between the experimental kind of world and constraints versus the constraints that we bring from nature, and I think there's always a bit of a tension. I've had discussions with Tim Holland and Roger Powell and others over the years about this, and I see there's kind of no easy answer to this. I would agree with Jacob that right now probably the best role of these natural databases is for testing. And yes, there's complexity in nature. We all know this, and for all the reasons that Jacob actually summarized. But I think the two of us would come down to the fact that if there are really repeated, consistent patterns, that has to be telling us something significant. So take the example of the predicted mineral assemblage sequences at low pressure. This is something I've kind of been worried about seemingly forever. And one perspective is that the predicted phase relations, they are done based on a thermodynamic database and activity composition models that satisfy some experimental constraints and some other constraints. But I would argue that in some cases, they're not producing or predicting what is repeatedly seen. So there's a problem. So one response is, well, you've misinterpreted all your mineral assemblage sequences. Yeah, okay, maybe in this particular case, but if it happens over and over again, that tells me there's still a problem. So I've always kind of viewed that, there's uncertainty in the, as Dave Waters explained most completely the other day, there's uncertainty in the positions and the compositions and the values that you get out of these constraints. But if there's within those uncertainties, you can vary the best patterns, the parameters to better satisfy the repeated patterns. And to me, that's where the two worlds kind of merge. So yeah, that's pretty well all I have to say on that.
Thanks. That's I would say a very modest answer, because maybe what we are missing is something like that, this kind of database to really go one step further in the calibration of those models. So, but I want to move on, and I have a question for both of you again, and it's more on the comments on the metamorphic phases, and it comes from Matt Cohn. And he says that the metamorphic phases concept simply says that the observations are repeatable. It doesn't imply anything directly about equilibrium. So for example, if the amount of overstepping is the same, and this can be debated, we will see exactly the same thing repeatedly. Even so, there is no equilibrium in this case.
Oh yes,
on that.
I really like that comment. So I think Matt is absolutely right, and I wish it were stated more. The metamorphic phases principle is observations. It's repeated observations. It doesn't actually say anything more than that. So I think I totally agree with Matt. The only reason that you kind of make the next step to equilibrium, I think, is that in order to explain repeated patterns, it would be, I don't know, if you imagine all the different kind of tectonic settings of, say, Barrovian sequences, if you look at all the different Barrovian sequences around the world, or even regional Buchan type sequences, each one has their peculiarities and specificities and rates of heating relative to burial, all that sort of thing. So to have that sort of consistency in the observations, like the sequence of mineral assemblage sequences, even though you can have these site-specific variations, you'd have to be arguing that the kinetics are somehow conspiring in a wonderful way to allow the consistency to be seen. So in a way, that's kind of one, maybe not complete answer for equilibrium. But Matt's other question is, well, maybe all of these boundaries are overstepped. And I'm going to flip down to a diagram from a paper that Frank Spear wrote with me a couple of years ago, if I can find it. Yeah, so this is a phase diagram that shows, this is for a metapelite, and it shows the equilibrium phase boundaries in the pale lines here. And then he calculated the position of the displaced curves if there was an assumed amount of overstepping required and how much you'd have to build up the reaction affinity to get to that. And that's what the solid lines are. And I won't go into all the details, but you could take that as an example where maybe all these metamorphic phases boundaries, they're all displaced consistently. And I think that's a fair question. I think you do have to point out that the nucleation of a garnet is going to be different. And so the amount of overstepping to make a garnet is probably going to be different than the amount of overstepping that is needed to make cordierite. And Dave Waters has absolutely shown this in his work. So it might not be quite as simple as that, but the general point I kind of get.
Okay, I have a live follow-up comment from Matt, and maybe Jacob can comment on that one. Even the overstepping models represent transitions between equilibrium states. So although the modes, relative timing, etc., might be affected, chemical patterns like iron-magnesium partitioning would be expected to be consistent. And this was a very important point of Jacob's presentation.
Yeah, no, I think that's a great point from Matt. I mean, yeah, I've made the assumption in the presentation that it's an equilibrium system. And so I can make the comparison between what I'm observing with the thermodynamic models. But if there is a greater, as Dave said, kinetic constraint, and Matt pointed out, you'd still see some, I don't know, episodes of reaction, and you flip from equilibrium to equilibrium perhaps, and so you might see these things. And that's the kind of thing that we can start to analyze in this database, because we can look at all of the mineral compositions in specific zones and compare, well, when you pass above the chlorite out reaction, is the biotite composition and the garnet composition similar at different pressures and temperatures and above there, and then does it change again at the muscovite out? That's perfectly viable for us to look at. I'll let Dave comment further on that.
But the implication might be that most of the reaction we're seeing is in fairly discrete intervals, such as by these mica-consuming reactions. And maybe like when you're in the amphibolite phases, maybe it takes a real overstep before, say, I don't know, what would be a classic assemblage, a kyanite, garnet, muscovite, biotite assemblage, one of your favorites. Say you decompress that, you might have to really decompress it before you build up enough energy to get it going. So I would just anticipate these kind of, I don't know, episodic, not exactly equilibrium transitions that are partly linked to getting the thing going from a bit of overstepping.
Yeah, that's a good point, Dave. I have another associated comment. Jacob, you speak about series of phases. Would those be better called index mineral series sequences or zone series? And the next question is, are these series actually Douglas Carmichael's bathozones? I'm not sure I know this term, so maybe you should.
No, that's good. No, that's excellent. I know both of those. That's fine. Yeah, no, I mean, I can ask, Dave can clarify why you called them Facie series in your original paper with Bob Tracy, but I thought that was after, the terms of, I mean, you called them Facie series, but if I remember reading it correctly, you say as in Huyton in 1961 and Meerschaert in 1961 and Huyton in 1965, and then alongside it's the Bathazone. So I mean, yeah, Facie series, index mineral assemblage sequences.
Yeah, this, I mean, the history for that was, it came down to discussions with Ben Hart, actually. Yeah, so the idea of Facie series, I think it's just, I think that goes back to Heaton, and essentially it is index mineral based. So you could call them mineral or index mineral sequences, or metamorphic zonal sequences based on index minerals. I think that'd be fair. I think it's just a different term for the same thing. But there is a difference with the Bathazone concept. And Dugald Carmichael made this pretty clear in his 1978 paper. Yeah, okay, nice. So that's the classic Bathazone diagram. So the idea of these Bathazones, they're just focusing on individual intersections. Like take this 1-2 intersection here. This is the muscovite quartz breakdown, and there's the andalusite sillimanite boundary. So you can actually write balanced, they're not really reactions, but they're assemblage balances above and below that point. That's not really telling you anything about what might be happening at lower grade or higher grade. It's just this intersection is, it distinguishes between a higher pressure and a lower pressure mineral assemblage. Now, you can extend that if you imagine that you have a prograde sequence going underneath that intersection. Say you first cross the muscovite quartz out, you make andalusite, and then you make sillimanite. That's kind of like a mineral assemblage prograde zonal sequence. If you go above it, then you'd have sillimanite comes in before the muscovite quartz reacts to make the K-feldspar, and that would be kind of a mineral assemblage sequence, or you might call it a Facie series that goes above it. But the strict definition of the Bathazones, like these bands that you get, are based on the particular intersections. So they're kind of linked, but in detail they're based on slightly different reasonings. And yeah, Dugald could probably expand on that a bit.
Yeah, and the examples that Dave was giving there of this intersection here, this is exactly what I showed in the talk. This would be a Facie series 1C, as we call it, and then above this line would be a 2A, as I gave, if you want to go back to the slides and look.
Oh, thank you for the clarification, both of you. Maybe Dave, can we come back quickly to you, because overstepping as a topic generated a lot of interest in the questions. So my question is, to what extent may the required degree of overstepping and kinetics be governed by crystal defects?
Crystal defects, okay. Well, the short answer is I think it could be affected quite a lot. But I'm getting to the fringes of my familiarity. I'm kind of a petrologist, and I recognize the importance of kinetics, but there are people who've done this more seriously than I have. To me, if rocks are deforming, then you're distorting them, maybe creating crystal defects, perhaps damaged surfaces that provide more favorable templates as places to where chemical ingredients can coalesce in the right proportions to form clusters that might form nuclei. So I guess it's just kind of a general feeling that in a rock that you're deforming, you're creating more favorable high energy places where where that nucleation process could take place. I might actually, if Dave Waters is on the line, he's thought a lot about this, and others have. Matt Cohn would also have thoughts about this, and Frank Spear, but that's pretty well all I would have to say. I don't know if Dave wants to add anything or not.
Yeah, I can chip in a bit. It occurs to me that an awful lot of the nucleation is going to depend on what happens in the grain boundary region. That's unless there's a really good mineral template, but then again, the nucleation may happen on a mineral template. So, you know, we just need to know more about what it's like in the grain boundary region. I mean, one thing about the grain boundary region is it's a sort of more disordered region, obviously, than a mineral structure. And if you can create a nucleus that creates order out of disorder, then that's something that will help. And so, you know, a lot of our nucleation events may be quite fluky things in terms of, you know, it just so happens that this spot on this particular grain boundary has the right properties and perhaps also just locally the sort of right nano composition to start the thing going. So it's going to be sort of, you know, a sort of nasty statistical, you know, thought process to understand how that might work. And I guess deformation is going to, you know, potentially create new areas of disorder or defects and things, and that might also help. And that's my feeling anyway. That is going to help the nucleation process and bring overstepping down.
Thanks for the detailed answer to both of you. Dave Pattison, now after your presentation, we have participants wondering, and I would say I'm wondering as well, would such overstepping be happening in our experimental setup as well? And in this case, would that mean that our thermodynamic models are based on experiments that already implicitly account for overstepping?
Okay, well, I would make reference to an absolutely fantastic paper by John Ridley and Alan Thompson, Ridley and Thompson, 1986. It's in the reference list to my presentation. And they're not the only ones who've made this point. Dave Ruby also made it. But if you look at the experimental literature, there are studies which look at mineral transformation in seeded experiments versus unseeded experiments. So this problem has been recognized for a long time. Like seeded experiments, the classic reversal experiments, like you mentioned in your talk earlier, that basically eliminates the nucleation process in theory, because you have all of the reactants and products. And so you're really just looking at differences in growth and consumption of the phases, but the nuclei are there. But if you compare those experiments with those which are not seeded, then there are really quite significant differences in the resulting position of where these mineral transformations occur. Generally, they're displaced up temperature for the unseeded situations. So they did a completely separate kind of analysis of seeded versus unseeded experiments to address this nucleation problem. And you know, it's one reason why there's kind of a recognition that the reversed experiment is a very important thing to do, and that unreversed ones are much less reliable.
Oh, thanks for the clarification. I think it's an important one. Another question for you, Dave. Can you propose a way of calculating oversteppings of compositions in a single solid solution? So for example, a sodic muscovite's metastability with respect to a low-grade fungite.
Oh, let me just think about that. Can you predict? Gee, I'm not quite sure. Like, in other words, if you had a slate or something that had a phengitic muscovite, and then you started heating that up or burying it, could you predict how much, say, overstepping you would need before you could start to change its composition, like not nucleating anything differently, but just like internal compositional changes within a pre-existing white mica? Is that the idea?
I think so, yeah.
Yeah, that's something I've really sort of thought about quite a bit. Jacob and I have discussed, and Tim Dempster at Glasgow, he's done studies trying to compare the predicted amount of change, say, and I think it's more the Chermak content. It might be the sodium potassium change too in white micas when you go up grade. And if you look at the energetic driving forces for these subtle changes in composition, which we predict out of these phase equilibrium models, you have to think that those driving forces are up against, in the case of Chermak exchange, you're actually breaking down tetrahedral bonds if you're going to be changing the Chermak content, because there's an aluminum silicon exchange there. So you have to ask, is there enough of a free energy driving force predicted in these subtly changing mica compositions to overcome the kinetic impedance of rearranging all these elements in these sites, including tetrahedral sites? And I've always felt that seemed really unlikely to me. This extends to plagioclase too, actually.
Absolutely.
Thinking of your like, to me, those plagioclase maps that you produced showing the zone plagioclase, to me, that's a really, like, a very sobering thing, because a lot of that plagioclase is not kind of chemically communicating with the system. But I'm getting off topic. Anyway, maybe you can predict it. Maybe you can predict it, but I sure can't. But I would expect you'd have to have, quite an energetic overdrive before you're going to get those micas internally changing their composition.
That's great. I fully agree with you. The coupled substitution is much slower than a substitution on one crystallographic site. The difference with biotite, for example, between white mica and biotite. I'm going to show tomorrow a few maps of white mica, and this will illustrate exactly this point. Let's move back now to Jacob. Jacob, simple questions. Are your database of natural data available for me to compare my own data against your data?
Yeah, no, that's a good question. The answer is not yet. Yeah, we're still in the, I suppose, interpretation stage. Whilst we have all the data, we're doing the analysis ourselves. The ION2, ION3 database, I'm doing the revisions as soon as I'm done with that on that. So that will hopefully be out towards the end of the year, and people can use that if you're interested in ION2 and ION3 and those minerals. The Hollow database and MetaP-Lite database a little bit after that, and the MetaBaseLite database sometime in the future. But I think what I'd like to say is that, yeah, hopefully these will become things in the public domain, because at the end of the day, this isn't, as much as it's Dave and I's work that we pulled them together, it's the hard work of all these other petrologists that have come before us, have gone out, sampled these things, taken the analyses. And that's really obvious in the wet chemical work, separating these minerals and taking them and dissolving them in these acids and whatever to get these values. And so I think the data belong to the community. So at some point in the future, I won't give you a date when they will be available for you to compare to. Yeah.
Wow, great. That would be an amazing contribution and something that we really need to have all the data organized in a way that we can easily use them. I'm going now a bit off-road. I have a personal question for you, Jacob, on that aspect. If we have this huge database, do you think that simply going for a machine learning model like this complex neural network would not be better than using this Gibbs energy minimization for where 1 joule or 1 joule can change completely the assemblage?
Yeah, no, that's a really good question. Yeah, and there's a change of how we go about it. Let me think about that. I think all we can do is try it and see. And if we have all of the information and the data, then we can move towards a neural network model and see if we can compare the two, and what are the predictions, and are they better or worse or different in certain areas. I think that's all we can do. But yeah, hopefully that's what this database will provide.
Okay, thank you. Now the question that is a bit tricky for you. You have tested in your example four different data sets on your natural data. And of course, everyone here is wondering if you have a preference among the 4 data sets, and which one would you recommend maybe to us to use?
Yeah, okay, right. Well, I'm not going to specify a preference here, so I don't get lynched later on by somebody. But there are pros and cons of each of them. So you know, if you want to include iron 3+N members in Staurolite, Biotite, I don't know, Muscovite, you've got to go and use dataset 6 because that's where the solution models exist. However, there might be issues in dataset 6. You've got to consider how have they incorporated these iron 3+N members? How robust are the thermodynamic data that sit behind them? Are there any thermodynamic data that sit behind them? Perhaps might be a better question. And you know, that's a complex thing. Then you can compare that to the older dataset 55 database, and that reproduces certain parts of my assemblage field better, in my opinion, or is closer to what we observe in nature. But there are other issues in you know, we looked at the silica content in the biotite and the muscovite. The variation in silica content in biotite was much less in dataset 6 than it was in any of the other older datasets. So perhaps that's a better constraint there. And that's just in the metaPelites. You know, if you want to do ultramafics or mafic melting, you've got to start to look at perhaps dataset 6. And so there's no single preference. I think, as I kind of said in the conclusion, just experiment. If you're doing your modeling in one of these Gibbs free energy minimizers, it does not take long to convert your bulk composition into the format and, you know, change it to dataset 5 and run the solution models in that just to see what the difference is. And I think everybody should be trying to do that. Yeah.
That's a fantastic point. And I think one of the key message of the workshop, and we'll come back on that tomorrow, is really to give a try and compare, and try to compare what are the predictions and what you observe, and try to understand maybe why you can't reproduce the composition that you observe, because maybe the model doesn't allow you that to do that. And it's a great point, Jacob. Now back to Dave Pattison. I have a question for you. If I talk with someone working with magmas and working with kinetic models, and they will immediately tell you that the most important variable is the time. And you quickly mentioned in one of your presentations the effect of the heating rate on the degree of overstepping. But my question is, how is the variable time considered in your affinity calculation? And if it's not, why is it not important for us?
Well, time is not considered. I partly addressed it just, I don't know, do you have this image on your screen?
Yeah, still sharing.
Yeah, so no, heating rate, the faster the heating rate, one generally thinks that you might get a bit more, you'd overstep a little bit more. The one point as far as nucleation is concerned is that might not be so important, and compared to the degree of the overstep. So yeah, these reaction affinity diagrams, they don't have time. They're really just plotting energies, like energetic overstepping. And you know, the rate at which that energy dissipates and triggers a reaction is not really specified. You know, there are experimental studies which have looked at temperature time studies. There's a whole kind of literature of temperature time rate of reaction studies, which I can't really give you examples of right now, which would address that. So time is sort of involved in it. I guess it's the time aspect would be the rate at which, say, heat is added to a metamorphic rock column. And so it would translate into heating rate. So it would have to somehow be translated into kind of an energetic value.
Now we are getting very, very, very close to the half pass, and I propose that we simply stop there and we conclude there at this point. Maybe let me quickly say something. We have seen a lot of very nice strategies to do these models. And I think the presentations today really showed us that the most important thing with the models is to try to reproduce nature. And you both pointed that out very, very nicely. And I think it was a great message for the participants.